Kenneth, thanks for having me here. So we're going to have a little bit of fun going through some of my history of playing with threads and concurrency, some of what I've kind of learned and what I kind of want to deal with. And I think this is a good thing to sort of start describing it. So about 4 weeks ago, I was in Brazil, and this is Sao Paulo. This is what the traffic is like there at times. It's just absolutely insane. And I get to see lots of concurrent applications, and when you see threads in these applications, this is not an unusual situation. Like many of our applications kind of end up in gridlock. And actually, if you look at this a little bit closer, what direction is that van going? Like, when you're debugging multi-threaded applications, it's often the case, it's like you find a thread, you go, what's it doing there? How do you ever get to that point? And so we end up sort of trying to make sense out of this craziness in our sort of parallel concurrent programs and stuff and all. So let's kind of like look a little bit of why do we do this? Like, are we crazy people who just want to make our life difficult by playing with concurrency? So what are the main reasons we want to do this? Well, kind of one of the things we want to do is make stuff resilient. So actually having more than one copy of something happening is a good thing because one of them dies, another one can take over. But also, the major reason we do this is for performance. We make things go in parallel, we hope to get more performance. Although sometimes we hope, we don't actually measure, and many times we actually go much slower than we expect. In fact, actually, there's some really good research, so not really going to touch on it here, but like, I'm going to talk about concurrency, but it's fascinating how we jump to it too quickly. There's a great paper by a guy called Frank McSherry, and it's called the cost paper. It's the cost of going parallel over being single-threaded, so the cost of what's doing that, and the research from that was really interesting, where they were comparing lots of different parallel algorithms, and people were arguing about one was better than the other. The fundamental mistake they made, and this is kind of typical, like, if we call ourselves scientists, we're pretty much lying to ourselves, because any science and experimentation, like, one of the things you do, like a medic would never sort of run a drugs trial without a control group. So if you're going to do any software benchmarking, you should have a control group. And if you're going to do a parallel algorithm, like, what's the perfect control group? Single-threaded. Like, you want to beat that. All of this research that Frank went through and showed, he showed that basically all these different algorithms were comparative. None of them compared against a single-threaded alternative. And the single-threaded alternatives were scary. In virtually every case, they beat the parallel cases. So if you kind of like want to go off and have a good paper, it's kind of fun on this. So let's look at this from a different perspective. So that's kind of throughput, dealing with different things. I'm kind of quite interested in response time. So I spend a lot of time in finance, and I'm sure a lot of people in this room have worked in finance, and we kind of care about latency and response time. And kind of why do we care? Because particularly if we're in a market and we don't respond well, it's kind of okay if you respond well most of the time. It's the times when we don't, it's kind of embarrassing. And it can kind of hurt and things can kind of go wrong. Another way we can look at this is that if a system doesn't respond in a timely manner, it's effectively unavailable at the time when we need it. So these are some of the reasons why we care a little bit about response time. What am I going to cover today? Well, I want to cover a bit of the theory behind parallel and concurrent systems, why we do some things, and then we're going to kind of go into a kind of quest of the last 10 years where I've played with different concurrent data structures to try and hand things off from producers to consumers, and what we've learned on the way, and kind of where can this research go next. So let's start off with some basic theory. Who can say they know the difference between concurrent and parallel? Who can comfortably put their hand up and say they know that? There's a few people. I'm kind of even hesitant, and like, my degree is computer science. My major elective was parallel concurrent systems, and sometimes I'm not sure. But actually, if you look at the research, and look at people who are experts, even they say confusing things. I kind of like how John Gustafson says that he actually never tries to compare concurrent and parallel because he thinks they're two different things. He likes to talk about parallel being the opposite of serial, or the fact that concurrent is the opposite of sequential, and things like vector is the opposite of scalar. So it's actually better sometimes to look at it from that way. That's one way of describing it. Kind of one of the ones that I really like is Rob Pike's discussion, so Rob Pike of Go fame, and particularly I like to highlight the dealing. So concurrency is about dealing with lots of things at once, where parallelism is about doing lots of things at once. And kind of teasing those apart actually really helps you sort of reason about this. So we find that we often have to deal with concurrent access to a resource, and that's where the fun and games usually starts, because if it's just pure parallel, it's generally not too bad. So let's try to split this down and look at it and work out, well, what is concurrent, what's parallel? So we typically have memory in our machines, we have CPUs, and we want to deal with them. We put the data structure somewhere in our CPU, some shared resource that we want to deal with. If we have a single thread of execution and it's running on one CPU, dealing with one structure, is that concurrent, is it parallel? If you kind of think about it, well, nah, it's nice and simple, it's not concurrent or parallel. And here's an interesting one. So we have one CPU, we're dealing with the same thing, but we're dealing with it in a time-sliced view. Is that concurrent or is that parallel? If you ask the question. Well, kind of interestingly, it's not parallel, but it is concurrent. So we have to deal with it. We're dealing with it at the same time, but we're never accessing it at exactly the same time. And so time slicing makes a lot of this interesting. We could be dealing with two genuine CPUs at any given point in time, dealing with the same data structure. Again, you ask the question, is this concurrent or is it parallel? Kind of both in this case, so that kind of makes sense. Or we may have the case of we've got completely independent things we're dealing with. We've got independent CPUs. Have we got concurrency or have we got parallelism? Well, we've got parallelism, we don't have concurrency. That's kind of, yay! That's a great world we want to be in. We start splitting things apart. So that's a kind of quick whistle stop. Let's look at this from dealing with request to response, which is a bit more interesting. So typically, we've got a request coming in. We need to do something. So let's take its little journey of its lifetime. We have to do some I/O. Yeah, we're typically having to decode that thing. We've probably got some pretty vile format that's come off the wire that we have to parse into something we know how to deal with. It could be something nice. It could be something like fixed messages which aren't very nice, or JSON or XML or something pretty nasty, but we take time parsing it, so often a very long time parsing it. Then eventually we're going to do some compute. We'll do some compute, we'll work on some data structures to basically do the main purpose we're computing in the first place, like usually do some business logic. There'll be some result of that we need to archive to keep for later. We need a transaction log of that somehow. We'll encode a response up, and we'll send that request back to the user. So very simple little request-response scenario. We'll send some data through a system. If we typically go with one thread on that, it's actually a nice, simple problem, but it starts to become quite slow. We'll have queuing theory, we're waiting, there's a lot of steps in this process. So we run to be in parallel or concurrent to try and speed this up, and there's a number of techniques, and this is what I find kind of fascinating. So the first and major way we kind of approach these things is we go with coarse-grained parallelism. So the single-thread case would have been great, but we want to get more throughput. So we throw lots of threads at the problem. Lots of threads, big thread pools. It's just your typical web container, Tomcat server, whatever it happens to be, runs at it in parallel. All of those different threads. Something to start thinking about at that stage is we have CPU caches, and CPU caches are the main thing that gives us performance these days. Our CPUs are so fast, they spend most of the time waiting on being fed data. If data is in the CPU caches, they're really quick. You kind of go and you look at this previous example where a thread starts off, it does every single step of the process. It then goes back and it starts all over again. It's constantly churning the cache. It's not cache friendly at all. And we've got a few other issues with this. So we also got to think about concurrency, because we've got data structures now that we're having to deal with for multiple threads. We need locks, we need mutual exclusion, we introduce a lot of complexity. We end up queuing on a lot of that. We end up having to write the storage, we bottleneck on these things. We get lots of really difficult problems to deal with. Yet this seems to be how our industry's gone off designing these sorts of systems, and that's the kind of de facto way things get built. I've been finding that every time certain requirements are very difficult, and by difficult requirements I'm talking about performance, security, reliability, all of the qualities of service, these sorts of designs fall apart incredibly quickly, and they all start evolving to a different type of design. And this different type of design takes a slightly different approach. So rather than that big pool of threads that you had before, you tend to allocate a thread per stage. You look inside a CPU, it doesn't start out and take an instruction and the same thread of execution runs with that instruction right through the whole thing. It forms a pipeline. One part will do the decoding, one part's already fetched it before that, then it'll execute it, then it'll retire, and then pass off. Look at the real world. You go to a factory, look at how humans organize ourselves. We organize ourselves into pipelines and we do things like that, and it works really well. Yet we don't do this in software very often. I find it kind of fascinating. By moving to models like this, what sort of jumps out, what becomes interesting? Well, to make things go well, we need to put buffering between them. So we have queuing where we're handing off from one thread to another because things run at different rates. We have to deal with this. But let's start looking at the question of concurrency now. So things like our nice big data model that we're having complexity through concurrently dealing with it. There's only a single thread dealing with it now. It's much more simple. I no longer have multi-threaded access to that model. I don't need logs. I don't need all the protections of that. And it's much simpler to deal with. I don't have that weird van that's somewhere at the traffic jam pointing the wrong way and I'm having to explain it. Because I can see this, I can test it, I can deal with it. You start looking at, well, what about the things that were a bottleneck, like your database or your file system or whatever? Well, now because you've got everything lined up in batches, you can, sort of the queues are coming, you can deal with them in batch. You can take a batch of things off and store them. You can coalesce things and deal with them. And all patterns start to evolve to these sorts of things. You can use them much more efficiently, we can understand them much better. And we start finding that basically these caches, the pipelines, the ability to batch, these are the things that enable a lot of the software to be much more efficient. What I also find is a very useful byproduct of it, it's a lot easier to deal with. So people say, well, these really fast, really complicated systems, they're going to be complicated. They tend not to be. They tend to be incredibly simple and very easy to deal with, as opposed to those scary systems where we've got these threads running from the thread pool dealing with everything and the whole complexity of dealing with that all the time. So we have to build interesting structures to be able to get to this point. But if we've got issues, what is the cause of issues? We usually end up with something preventing progress, and we can kind of ask that question of ourselves a lot when you're designing these systems. What is preventing progress? If I want to go faster, I have to find out what it is. And it's usually something is blocking you, and a thread that is blocked cannot make progress. So when you look at it from the concurrency perspective, that's the thing we care about more than anything. What's the blocking? What's the cause of it? Blocking tends to have one of two major types. There's the systemic pauses you'll get in your systems. These are kind of interesting. This is where like your JVM stops, your C# runtime stops, anything like that, where you reach the point where a stop the world event has to happen because of garbage collection, because of lock revocation, because of all sorts of really interesting things that happen inside our VMs. But it's not just our VMs. Our operating systems have a lot of these issues as well. Things like transparent huge pages being on by default in Linux, where we've got pages now of different sizes. We've got huge pages, we've got normal pages. We end up sometimes with a memory heap that looks like Swiss cheese. We can't fit our big pages into those spaces. We have to compact it. That is pausing. It's compacting the same as garbage collection inside our runtimes. That can take time. We can even have our hardware stopping us because we get things like system management interrupts, where the hardware will stop the processor occasionally to take its temperature to see if it's had errors, to check various things, and we can't even control these at an application level. We have to deal with them. That's an interesting subject. We could talk about it for hours on its own, but I'm not going to talk about it for this talk, I'm just making aware of it. The thing that I'm interested in for this talk is concurrent algorithms, because the other main cause of blocking is one thread blocking another. And these are the things that we have the control over when we're programming day in, day out. It's things like when we notify one thread to another using condition variables, we're using all of the different concurrency primitives we have, the locks for mutual exclusion, we're using rendezvous, whatever it happens to be semaphores. So I've spent a lot of time working with these things, and the next section is really about what is the quest over this time, kind of what have we learned and where we can kind of go to. So the reason I got into kind of pipeline systems is I was working on betting exchanges over 10 years ago. So if anybody has an experience what betting exchanges are, because you're in the US where this isn't allowed. Most of the rest of the world is actually quite common to have gaming and gambling. It's effectively finance, but with a different regulator. Like, I spent a lot of time in finance and I spent a lot of time in gambling, and it's exactly the same problem, it's just a different regulator. And to be honest, the regulators are better in gambling, a lot better than they are in finance. So if there's any financial people here who do regulation, I'll run away at the end. But I've actually been a registered bookmaker, and I've been the regulated entity in a number of organizations. I was the person who went to prison if we broke the regulations. So I became very aware of what the rules are around a lot of this. But we were building systems, and so one of the systems I was involved with was Betfair, and just for context, Betfair used to process more trades per day on their sports betting exchange than all of the European equity exchanges combined ×2. And so you think this sort of little gaming, gambling thing on the side is small, it's really significant in many ways. So we were trying to build these things that were really fast. We were looking at SEA, looking at all sorts of interesting things, but we've done a lot of work that led us, basically pipelining was the answer to do this. This is the only way you could run the right sort of transaction volumes that were required. And we learned a lot about what blocks threads and what we needed to do for handoff for these buffering and queuing disciplines. And so I learned a lot about the evils of this. And let's look at some basic Java and the impacts of this. So the good old Java queues, when we start dealing with them, most people start off with put and take. So you put something into a queue to hand off to the next stage takes out of the queue. These are blocking operations by their nature, so you're going to put into the queue. If the queue's full, you block, you're waiting for enough space, and then you can deal with that. They signal either end using condition variables underneath. This is how they fundamentally work. So if you stracer, you sort of dig right down into the kernel what's going on, you will see they're calling condition variables underneath. Now, it appears to us as wait and notify on synchronized, or calling signal and await on a condition variable at the Java level, but they all map down to these condition variables underneath. And this involves a scheduler to hand off. And when it comes to sort of working out how expensive these things are, who thinks that a condition variable is more expensive, or let's say so, who thinks it's less expensive than a network call between two machines with one of the latest networks? Should it be less or should it be more? So two threads, handing one thread to another, condition variable, should that be less than going between two machines, user space to user space for a message? Should be less. Do you think it is?
I hope so.
It's not. It's actually slower than doing this with some of the latest networks. So let's measure it. Let's see what it's like. So if I put together a little test, and what I want to do is I want to signal from one thread to another that something's ready and signal back in return. So simple round trip, not even transferring any data. So there's not even serialization of that. And I want to put every single response in a histogram. And so I don't care about averages, because averages lie. Averages lie an awful lot. We want to know really what the distribution of results is. So I'm going to put the results into a histogram. Let's see what this looks like. So between two machines, 90% of them will happen in about 8 microseconds. This is on a very fast, well-tuned machine. It will take about 8 microseconds for doing that round trip. You can do that round trip in a few microseconds less if you're using some of the latest networks with kernel bypass technology. So it's actually faster between two machines. This is not a really good place to be. But then, look at the tail. This gets to be much worse. So beyond 99, you're going up and you start going into the tens of microseconds. And actually, the worst case scenario is over 5 milliseconds on a simple run. Now this was measuring on a machine that was doing nothing else, it's really quiet, and it's well tuned. So that's actually the really bad news that has to come with this, because if you measure real world systems and you're doing signaling with condition variables, I typically see averages of around 50 microseconds with outliers up into the seconds at times. So signaling between two threads using condition variables, you start to realize this is not a good place to be. And after you realize that, you start looking for what are the alternatives? Where do I go and look at next? So you think, well, let's look at the non-blocking APIs, because the non-blocking APIs don't use the condition variables. Is this going to be better? I mean by this, offer and poll, where you offer to the queue if the queue is full, it returns false. So you can go do something else or you can try again. Pull is the same on the other side. You pull from the queue. If there's something in it, you get the object. If there's nothing available, it returns null. So it doesn't block, but it undergoes this. So for the rest of the talk, all the benchmarks, just for reference, were done using a fairly recent version of Ubuntu, latest version of Java, and you can go and test all these benchmarks for yourself. So one of the things I'm kind of believe in good science is you should make your stuff out there so it can be independently verified by other people. That's good science. That's what we should be able to do. So what did I go and find whenever I tested some of these things? So what I want to do is a couple of tests. So this kind of big wall of numbers here is showing me that I want to test the three kind of amigos that you get inside the JDK. The array blocking queue, the link blocking queue, and the concurrent link queue. How do each of those perform if we're using them in the non-blocking way? Like we've seen the blocking way before was terrible. Let's see the non-blocking way. See if it's any better. I want two interesting figures here. I want to know what the mean is, the average, because that gives me a good idea of general efficiency, but I'm also much more interested in the outliers. And I'm picking 99 percentile here. There's really interesting stuff beyond 99 percentile, but that's generally not related to your algorithm. That's related to the systemic pauses that I was talking about before, which are important, but they're kind of out of scope for what I want to deal with here. So what does this burst length of 1 and the different columns mean here? So for a burst length of 1, what I want to do is send one message into a queue, pick it up on the other side, and echo it back again. So I'm just doing that over and over again. So I'm only going to put one in at a time, get one out. So it's only a burst of one message. I want to try this with one producer, two producers, and three producers, all competing with each other at the same time. So they're not taking turns. They're going to be genuinely concurrent and genuinely parallel. So they're going to go and come and hammer on this. So we have to deal with that contention. And at the very top, what I've got there is a baseline, which is my control group, to see how these do against. It's a variation of an algorithm that's going back to the 1970s by Leslie Lamport with some influences from fast flow, and it is the fastest single producer to single consumer array queue I've ever measured. And so that gives me the baseline for how those are comparing. So it on its own is doing the round trip in 167 nanoseconds. So that's how quickly we can be handing between two threads using these sorts of techniques. You start looking at array blocking queue and link blocking queue, we're getting reasonable figures here. But what I want to get into is the more interesting case. So if you go back to the one producer, one consumer, or just so one message in, one message back, it's very unrealistic. You actually don't get that much concurrency. You don't get much interleaving of what's going on. And the real world's not like that. The real world, traffic comes in bursts, and it's quiet, and then it's burst, and then it's quiet. So what I want to do is I'm going to send in 100 messages and get one back. Send in another 100 and get one back. And that way they all have to interleave a lot with each other. By doing that, we really do test the concurrent algorithm much better. We see the effects of this. And some of the stuff that starts to stand out quite quickly is like, look at the 99 percentile on link blocking queue and array blocking queue here. Is you start going up into the 90 and then into 180 microseconds. That's many, many round trips between two machines. So this is really not looking very good. Concurrent link queue is much better than those others. And so if you start building these things with the standard JDK stuff, you very quickly gravitate to concurrent link queue as the better way of doing that. And then the horror of what it brings to you starts to appear. Because you start realizing with it being a link queue, we can't have back pressure because we can't limit its size. It's a linked list of nodes that can just keep growing. We can end up with out-of-memory errors. We can't query its size very well. If you do any performance analysis, you need to construct a model of what's going on. You need to have figures that goes into things like queuing theory to predict what's going to happen. So you need to be able to know what the size of the queue is, what the flow rates are. These sorts of things become important. And you can't measure those from the current JDK classes. So for example, let's take array blocking queue or linked blocking queue. If you call size on it, that takes out the same lock as the lock for offer and pull. So by reading the size, you actually block traffic. Not very useful. you would want to be able to observe without having an observer effectiveness as much as possible. So if you go with concurrent link queue, it doesn't do that, but it's an order n operation where it walks the whole queue across the links to do it. Not very good. And concurrent link queue also generates garbage. So in some of these high performance systems, you very quickly realize we can't use those. We need an alternative. So we need to go and look at what else is there. Let's just quickly touch on why something like concurrent link queue is actually faster than the array blocking queue or the link blocking queue. And that's because concurrent link queue is not using locks. It's using atomic primitives that do CAS, compare and set. And this is actually a very realistic model of kind of what's going on. It's like rather than having the coarse-grained stop some traffic, let some traffic go like you get with traffic lights, you get the kind of British model of roundabouts here, where you drive up and you can just make progress around the roundabout. You don't even have to stop. So these aren't like stop signs. You just go through them as long as nobody else is there. So there's sometimes blocking, but not always blocking. The problem with the locks is, if you're dealing with the CAS instructions, this is all happening just between the threads themselves. Go to locks, you need an arbitrator. And the way I like to think of this arbitrator is, if anybody remembers the Hitchhiker's Guide to the Galaxy, when I was young this was a really cool book and very funny, so I remember reading all of the series, but then they made a movie about it. And if you know what these guys are, these are the Vogons, and they're the biggest bureaucrats in the universe. Like, if you want to do something, like at one stage they try to catch the main sort of protagonist of the story trying to escape, and they couldn't give chase because they hadn't filled in the appropriate paperwork to go and do it, so they didn't get the chance to get him. And this is a bit like when you're dealing with locks. So you have to ask the operating system to arbitrate between two parties for who takes their turn. And that is a very expensive process because you're getting third parties involved. These sorts of models are much better, where we quite simply take a ticket for what our turn is, and you'll see that a lot of the algorithms that I'm going to go into are fundamentally based on this idea. There's lots of great ideas in the normal world that can inspire different ways of working on stuff. So if anybody's ever looked into the disruptor, you'll see at the core of it, you take a ticket and you take a turn. And I've had a lot of people ask me, where did you get the idea for some of this? Well, actually, it comes from Leslie Lampert's work in the 1970s on the bakery algorithm, and he was inspired by this sort of stuff. Like, a lot of the stuff is old, it's been around, it's not new. So let's just repackage and use it in a good way. So what I want to start off with is some basic inter-thread FIFO. So I want to exchange from one producer, from producers to consumers, but we want to do this in the same process across threads. Kind of what options are that are better. So one I can pick on quite well, because I was partially responsible for it, is the disruptor. So how does the disruptor work? Let's give a really quick overview for it. So what we do is, we start off, we need to claim our ticket at the deli. And we do that by claiming a sequence, and we do that with a CAS operation. So that's one of those atomic operations that doesn't require locks. This is one point where we can get queuing, because this is where we have concurrent activity at this stage. We're dealing with multiple threads on the same thing. So as one thing's using, the other thing's got to take a turn. And the way these things work really well, it's a bit like using get or a subversion. You basically, you check out the state of the world, you make the changes you want to make, and you commit back. If it's changed in the meantime, you fail, you check it out, you do it again. It's exactly the same model. I find it quite funny that most people say, oh, I can't do lock-free algorithms, they're really hard. Well, if you use get every day, you're doing it. So it's not actually that scary. You just got to be organized and do the right thing. So you claim your ticket gives you the slot that you can use. So you go and you use the slot, you put the data in that. The disruptor works by having pre-allocated all of the objects, so you can just use them over and over again. And then we're into the interesting case of, how do we say we're done? And in the original, so Disruptor 1 and Disruptor 2, we kept the second counter, which was the cursor that we had to update. And we had to take our turns of updating that as well. Once your update has happened, the consumer could see that the counters had advanced. By just seeing that the tickets had advanced, they know they can go and work with that data. They advanced their own ticket later on, and that way we've just coordinated by saying we're taking turns, and we just do it with numbers, and that's why we pass things off from producers to consumers. Really interestingly, so In the core of the disruptor was this little piece of code. And it looks very innocent. It is probably one of the worst bits of code I've let go into the public domain. So it's kind of good, you can point fun at code, especially your own code. So what's really evil about this simple little piece of code? So this is the bit where after you've claimed your slot, you've worked with the object, you're now trying to say you're done, and you're signaling to the consumer that they're allowed to deal with it. So this algorithm is really simple. You notice the sequence you claimed, you take one away from that sequence, and whenever the cursor has reached one behind, that means everybody else is caught up, you're good to go. And then after that's happened, you can update the claim sequence and move forward. So all it does is put everything into a line, and with everything being in the line, we can progress nice and cleanly. The problem with this is, you've got a thread, it goes into this loop and it's waiting for something else to catch up. But let's say between the first line and the while statement, the previous statement, the previous thread is running and it takes an interrupt because you don't have enough CPU resource. The operating system has taken the CPU away from it and given it to another thread, maybe given it to you to do this thing. Now the previous thread is not making progress. It's stuck now on the previous line. You're waiting for it to get there and you're wasting CPU resource in the meantime. What happens is the whole thing doesn't make progress. It's not coordinating really well. Now, this worked really well for us in LMAX for a while because we always had more CPUs available than we had threads that needed to run. So we didn't see this situation very often. When we released this as open source, lots of people started running it in environments where they had less CPUs available than they had threads that wanted to run, and you get into these starvation scenarios and things go horribly wrong. And you end up basically doing the double face palm when you realize how badly this sort of thing performs and how it works. So you kind of learn from your mistakes, you regroup, and you decide, how can I do this better? So what we did in the Disruptor 3 was, let's get rid of that concurrency. So what I want to do is, I want to go parallel, but I don't want to be concurrent. How can I get rid of the concurrency at that really nasty place that was happening? So if we go to sort of do this again, we claim a sequence, we've got the normal beginning steps, we work with the data. Now the interesting thing is now, rather than waiting on other threads and dealing with the concurrency, have you noticed now that rather than having a single variable, we have an array of variables which is what is available. Then we just flag that that's available. By just flagging that that slot's now available, we don't have to coordinate with the other threads. We're now parallel. We're not concurrent with the other threads as far as dealing with this one particular case. Then the consumer can just go ahead, because they're watching the available slot to see if something's available. They then use it and they take it out and they update themselves. Now what's this look like from a real system perspective? So Disruptor 2, this is a graph given courtesy of one of my clients who works in financial trading, and they were using the disruptor at the core of their trading system. It's obviously anonymized, but what you've got here is nearly 2 billion trades going through a given system, and every single one's recorded and put on a scatter plot. And this is a log scale. And what you start seeing over time is there's some interesting effects going on. We've got these weird spikes, and there's some stuff starting to happen out towards the end. We replace Disruptor 2 with Disruptor 3, and what happens to the overall performance, not just to the disruptor, the whole system end to end got faster. That's a log scale. It came down and got faster, and it also got rid of a lot of the peaky effects that was in there. Some of those big spikes were those times where the threads were getting stuck and waiting on each other. Whereas we get rid of the fact that we're blocking on each other, those are gone. Then we could actually see there's loads of other interesting effects in the system that we're able to go and work on instead. So like one simple change can so change a whole system. So we kind of learned a lot about that. We also see that some people want to keep a queue interface. So if you want to swap out one of the JDK queues, you want a different queue implementation, you don't want to go to something like the disruptor, you want something different. Well, can we apply the same ideas? Well, let's go get Delhi tickets again. It actually works quite well. So track a queue with a head and tail, and multiple producers can cast forward the tail to claim slot. They can put the item in the slot, And the really cool thing about this is we don't even need to have something that signifies that it's available. We don't need other counters because the slot itself being populated tells you you're done. A lot of these algorithms are all about taking multiple steps, and you know it's complete when you see a certain step's done, as long as they're done in a defined order. So we just work with nice orders. From this, the consumer can see the fact that that's in there, it can take it out, and it can increment its own counter to say it's done. Now, taking these algorithms, what does this look like if we compare to some of the previous examples? So what I want to do now is compare to the best of the previous, being the concurrent link queue. Let's compare the disruptor 3 and compare this many to one concurrent array queue. What do we get in figures? Well, first up you start noticing is the average case has got a lot better in the lowest, because you're actually doing a lot less work. It's a simpler, cleaner algorithm, gives you better throughput. But this is sending one in, one out. What if we put in multiple things? So doing a burst of 100 and sending back a single response. How does this do? Well, when you look at the 99% under contention, all the wins you've got all of a sudden don't look so good. And what you start realizing is if you've got a spinning cows loop, it becomes the great equalizer. And you generally end up, even when you do clever things with other algorithms, you end up being limited by the spinning cows loop. You've got to work out how do you get around it. And in doing this, they start looking at lots of other different techniques, and particularly, you start looking at, well, what shifts data really well, and does this probably better than anything else? And I think the network cards have got some of the best experience in this area, so let's just go and steal ideas from them. Let's see if we can take ideas from them and do it in a better way. So the fact that we're now going to start working with buffers directly and not objects, we can also do it off heap. We can do it between processes. We can do this in process, but also across process, exactly the same sort of way. So a kind of classic one for doing this is a ring buffer. And how would you do this with a ring buffer? Well, you typically have a head and a tail in a ring buffer, the same sort of thing, but rather than being slots, they're byte positions. And you serialize your objects into the ring buffer, and you move forward the head and tail seeing where you can consume. So how would you put something in? Well, you need to cast forward the tail to claim some space. So a producing thread will do a cast operation. Different threads are going to race with each other to do this, so you've got a slight weighting effect. But once you've cast the tail, then independent of the threads in parallel, you can copy in the message body. And then how do you know you're done? Well, you put a header on it, and if you do things in a given order, when the header's put on, you know it's ready. And then from there, the consumer knows that they can consume. So what they do is they consume a message out, and they can move forward the head. And that way you just move around the buffer, circular buffer, we use it over and over again. Really quite simple. What's a header look like? Well, you quite simply put a frame length and a message type, and then you've got the body of the message. You just define this as a really simple structure. You know you're done when you put the length field onto the message. And by putting that on last, you know how big it is, you know how to deal with it. If you don't put it up, by putting it on last, the field in there before will be 0, and that's how you know that there's nothing there to take. But this has the impact of something has to do the zeroing, and it's the thing that takes stuff out. So the thing you start learning from dealing with ring buffers quite quickly is you can get great latency from them, but they're limited throughput because you have to zero after you take something out. So you're always sort of doing twice the work on the consumer side that you're doing on the producer side. And as a result, you're then limited by the slowest step, and that's the consumer. So we started looking at, well, how do we do this better? How do we get over things like the spinning cas loop? Because we know that's a limiting factor. How do we get over the zeroing? How do we start taking some of those things apart? And so this is when I started working on Aeron and the IPC implementation, because we needed a handoff between different threads. So let's take what we know works well from ring buffer implementations, in that we want to allocate some memory and we want to add things into this. So what we typically do is we need to move forward a tail, put a header and a message on it. We do this a number of times, the normal things, but if you actually look at the different steps, so like we want to add the tail, copy the message, put on the header. That becomes a nice, interesting step, and if you do that, keep going on forever without wrapping around, you start getting some really nice semantics, but you get this problem of like one file that goes on forever becomes a big issue. So you end up with, what do you do with this if you've got the one file that goes on forever? Because if you do, you end up with this problem of having page faults. As you reach the end of the file, you're constantly page faulting, you get a lot of VM pressure, and you basically move the problem from the user space down into the kernel, and you end up with a big issue. So think, how do I get over that? Well, in the early 90s, I did a lot of backpacking, and the one thing I learned very quickly from backpacking is you travel light. You basically travel with wash one, wear one, dry one, and you go around and you just deal with things nice and simple like that. So if we allocate 3 buffers, you work with the current active buffer, you've got the dirty buffer that you've just filled, and you've got a clean one that you can end up using next. But can you get rid of the CAS in this? So that allows us to deal with the buffers. What about CAS? Well, on x86 and now with Java 8, we've got access to an instruction called axadd. And what an axadd does is it lets you increment a counter, giving you the value it was before without having to read and keep going around that loop. It breaks you out of that spinning CAS loop. So it's a kind of the thing, it's like, I want to commit to Git, make a change, but I don't need to check out and check back in again. I'll do it all in one atomic operation. So there's no room for someone to get in and check out in between what I'm doing. So how this works is you axadd the tail. That gives you some space. You get the value back to know where you started, so you know you can go from the start to the amount of space that you have. Another thread could also be axadding the tail at the same time. So those things are concurrent, but they're not spinning with each other, so they're just doing that. One can get some space. If you actually take the worst case scenario where you run out of the buffer, how do you deal with the rotation? Well, the one that won gets the copy in its message. It's there, it's out, it's done all of that in parallel. The one that tripped the end of the buffer, how does it know it tripped the end of the buffer? It gets the value that the index was before. It incremented it by an amount, so the value it gets back. If it's less than the end of the buffer, it knows that's within the buffer. It then checks with the length that it asked for, does that make it greater than the buffer? If that's then greater than the buffer, it's the one that tripped. If it was an index that was even greater than that, it just does nothing. So you can have as many threads as you want. You just agree to protocol to how they work together. So the one that realizes it tripped, it's responsible for just closing off the file by putting in some padding. It rotates to the next one, so that it just does that rotation around. We don't need a third party. We don't need the arbitrator to come along. And it puts in its message, and that's kind of great. Well, you end up with this interesting question about, what about the zeroing? Well, the fact that you've done this handoff now, you've got the dirty buffer. The dirty buffer now can be dealt with by a background thread that can do the cleaning. So now we can address the throughput. So we get some of the benefits of reducing the latency that we got with the ring buffers, but we also get rid of the throughput issues by making that a background thread issue. So what's this look like from a figures perspective? So simple burst case of one that's going in there and sort of comparing the different implementations. If we look at Aeron, it's actually a little bit slower than the basic ring buffer. Well, why is it a little bit slower in this test? Well, what we're actually doing is putting a much larger header onto this. So Aeron's designed to go onto the network as well as between threads. So the same buffers can be shipped across the network to another machine. And if anybody's into sort of distributed data structures, one of the latest cool things is CRDTs. The Aeron data structures are in fact CRDTs. And for anybody who's familiar with ITEF, which is kind of commonly known as protocol porn, that's the description that we have for it. There's everything in that header that allows you to reassemble the data structure on the other side of the network. When the packets arrive out of order, when they arrive in duplicates, it can deal with all of that. So this is why we take a slight increase in cost on the single case, but what's it look like when we start dealing with bursts? So if we send a burst of traffic into the machine, how does it cope? Well, the many-to-one case, notice we've actually had a step improvement over the last concurrent link queue. So we've had our first major step forward, especially in the 99% case. Why is that? It's kind of interesting. And that's because of an effect known as false sharing. When we move memory around our subsystems, we don't move a single byte or a single word at a time. We move blocks of data. Those blocks of data are known as cache lines. And so what you can get is, you can get data that's right next to each other, is causing the blocks to be pinging backwards and forwards between CPU cores and threads, and that effect is known as fault sharing. When we have the arrays for the array or the disruptor or anything like that, we've got elements right next to each other, because that's the nature of an array. It's all of these consecutive references to elements. By using a ring buffer, you've actually got things naturally padded out by the objects themselves, and so you change a lot of these effects. Also, this same effect impacts the garbage collector as well, so our garbage collectors are doing a thing called card marking to know which areas of the heap they need to look at. Things that are close together end up marking the same card. That has a fault sharing effect as well. So by going off heap, we avoid a lot of those fault sharing effects. But back to this other interesting question, what about the spinning cas? The fact that we got rid of the spinning cas, did that make a big difference to the performance? Well, let's look at it. We actually have a major step forward. So in the mean and in the 99 percentile, we are a lot better now on the burst scenarios, even putting that really large header on it. If we wanted to go thread to thread with a lightweight header, we can blow away the competition and make it much, much faster. So what's this look like kind of the last 10 years as a bar chart, because the numbers are kind of hard to get your head around. This is the round-trip latency in contended situations. We're down now to like burst scenarios being very, very quick, sort of down to a few tens of microseconds to do things really well. So it's a nice step forward. It's been a fun thing to do. Kind of where can we go next? The interesting thing is we're in a JavaSIG group here, and when we built a lot of the stuff, we built them in C++ and in Java at the same time. And I kind of had great fun. So I worked alongside Todd Montgomery for a lot of this. Anybody knows Todd from sort of 29 West and Informatica and different places? He's a really great C++ programmer. And I used to find it quite frustrating where we'd be competing on stuff, and I could beat the C++ by doing better algorithms, and then Todd would just copy the algorithm into C++. But what was kind of interesting is you can definitely beat native implementations by just good algorithms. The problem is they can go copy the algorithms afterwards, but the biggest wins are in the algorithms. Where are we kind of at now? So in the IPC implementation on a 3 gigahertz CPU, Aaron is now at, if you're shifting 32-byte messages, so nice small messages, which really exercises all of the machinery, we can do about 30 to 31 billion messages per second in Java between two processes on the same machine. C++ is about 33 million, which is a bit annoying. So they're a bit faster and a little bit lower latency. And why is that? What's the standout features on that? Well, we have these busy spin loops. And the way our modern processors work is when you're in the busy spin loop, they speculate and try to go forward. Every time you reach a branch in your code, be that a while statement, an if statement, sort of a switch statement or whatever, your CPU doesn't stop if it doesn't know the answer of the branch. Like, for example, if you do like, is I less than 7 and it doesn't know the value of I, it doesn't stop, it guesses and continues making progress. So it speculates and goes ahead. The problem is, when you're in concurrent algorithms and you've got busy spins, you don't want them speculating, because if they speculate and get it wrong, they have to wind it back and undo it. And that undoing is an expensive operation, so you want it to not speculate. There's an x86 instruction called pause that stops the speculation in those loops. We can get at it if you're writing C or C++, because you can just do it some inline assembler. It works really nicely. One of the nice changes we've now got into Java 9 as pushing on this is Java 9's got a new method coming on thread called onSpinWait. So onSpinWait, you can put that inside your loops, and it dramatically reduces the latency and also the power usage inside these busy spin loops. So we can start doing things like, we've done some prototypes of this on OpenJDK and Zing, and in doing it, it drops the latency of the disruptor 20% by putting these sorts of things in. So it's coming in Java 9 quick, so we'll have that. That's one of the things. The other thing that's actually much more annoying is a thing called data-dependent load. So these processors can speculate and run forward really fast, but they can't speculate past something they don't know. So if you hit an if statement and like I less than 7, it can do the then and the else. because they can speculate. If you've got a pointer to something and it goes to something else, you can't speculate past that because you can't guess where it's going. There is no means of doing that. So you want to be able to go to somewhere by dead reckoning if possible. And one of the annoying things that C and C++ can do that Java can't do is we can do stuff like embed an array inside another object, or we can embed a small object inside a large object where it's not a pointer dereference. We can get it by dead reckoning. You know, if I've got a reference to this object, I know that if I go X bytes forward by dead reckoning, I can get that straight away. So I've got that step taken out of the process, and I can make it a lot faster. How can we get this sort of thing in Java? Whenever we get value types, probably Java 10 or sometime in the future, we can start doing some of this stuff, like we can put the small objects into other objects. We can't do all of the cases. The really important cases actually become more complex in the layout, and object layout, the stuff that we've been working with the Zool and Giltene, will really make a lot of this easier. It also doesn't require a language change. So if anybody's got any influence on what we end up doing in Java, start leaning on things like object layout. It'll make a big difference for how we close one of the last big gaps in performance. Like in Java, we cannot build great data structures from a performance perspective. You try to build a good B+ tree, you will have too many data-dependent loads. It just won't perform anywhere near as well as it will on other types of languages. So we need these things. We also had some interesting discoveries around memcopy, where you're often copying things in and out of buffers. And I was finding there's lots of cases where C++ was like more than twice as fast as Java. And you shouldn't get that with things that can be jitted and intrinsified to being really fast. And within the cache subsystem, I was finding sometimes C was 10 times faster than Java. But sometimes, not all the times, and what we discovered this was down to was alignment. So depending on where buffer started and stopped, if there were multiples of 32, we were getting really fast factorized copies. If there were not multiples of 32 for the starting and destination addresses, they weren't dealing with that. Where memcopy in C was dealing with that a lot better. So like when we built there, and we had to do some interesting things where we forced some alignment and do some tricks, but it was really nice if these things were fixed in the JDK. And there is improvements coming where this has been addressed. It's been spotted in a number of places, and people are improving it. So some of the stuff is good, where we're starting to close some of the gaps. So that shouldn't be a language gap. That's just an implementation gap at the moment that we need to fix, where the mem copies are better in some of our native languages than they are in Java. But the real standout thing for me is how broken some of our interface design is. And so going right back to collections, when we've done some of our concurrent collections, when they extended the collections API, we made some fundamental mistakes, and particularly around conflation of concerns, and the queues are full of these. So what is one of those conflations of concerns? So imagine you're polling from the queue. The poll contract is, if I call poll, if something's there, I can get it. Now there's a difference between it's available right now and the queue is empty. It conflates the concerns of availability and is empty right now. So what you should do with a design like that is poll, if it gets null, you might want to check if it's empty because you could be partially through the offer on the other side. And because this is a multi-step process, if you've seen the start of the step, you don't want to get into this busy spinning scenario of waiting for the thing to complete. You're back to the mistakes that was made in the original disruptor. And the API actually forces some of these mistakes to be made, so even though people know better, they can't work around them. And then there's the other abominations, like if you look at all the code that's in most of the concurrent stuff, about 80% of it is dealing with things like remove on an iterator. Like, who in their right mind is going to iterate a concurrent queue and call remove? Like, we just shouldn't be doing things like that. So there's kind of some lots and lots of interesting lessons from the design perspective. So kind of wrapping up here now, what's in closing? Well, we have to deal with this nonsense of multiple threads hitting on something. Like, pipelines are not the only answer, but they are one answer I think people should consider more often. They make a lot of development a lot easier for quite a few different cases of applications that we end up designing, rather than going for this coarse grain parallelism, or coarse grain concurrency and parallelism together, and trying to manage all of that. Whereas we just do flows of pipelines with individual threads on those, not dealing with concurrency within them, and work on our data structures for doing the flows in between. it gets a lot easier. Where can you find some of this code? All the benchmarks, I'll put them up on GitHub. The data structures that are all mentioned, they're all there, they're all open source. You can go and have a play and have some feedback. You'd be really welcome if you want to do that. On that, I'll kind of wrap up and take some questions, if anybody has any. Yes?
Yeah, I've got two questions. First, when you're pausing the garbage collection, is the real problem that you're blocking all the other threads so the garbage collection thread can run? Or is it because the garbage collector is moving things around, it's flushing the cache?
So there's actually a couple of good points in that. So when we've got garbage collection, is this causing some of the problems? And a lot of how garbage collectors are implemented cause some interesting scenarios for us. One of them is the fact that not all of our garbage collectors are totally concurrent with the application. They end up having to stop our application for many steps of it, and that means we've got to bring threads to what is known as save point. And we have to wait for every thread to reach save point before they can progress. Interestingly, if you turn on all the GC logging for your JVM, a really important thing to turn on is not just all the GC statistics, but also the application stop statistics, so they actually know when your application stopped and not making concurrent progress. You'll see quite often that it's stopped for much longer than it's just doing GC, and that's usually the case when it's bringing the threads to save point. So getting to save point is an interesting issue. Some of how we code can cause part of the problems. So how does a thread know to come to save point? It does a thing called save point polling. And it checks occasionally, should I come to save point, to let the environment do stuff in the background. Where it typically does that is either the enter or exit of a method or the back edge of a loop. And it's only the back edge of an uncounted loop. So to do the runtime, our loops are one of two types. They're either a counted or an uncounted loop. And what is a counted loop? So once you've got a loop that's for I equal 1 to 100, that is considered a counted loop. It doesn't do a save point poll inside there. But guess what? For I equal 1 to max int is also a counted loop with no save point poll. You could run for 2 billion iterations without going to a save point. And that could end up being computationally expensive, especially if you're doing lots of cache misses inside those. Funnily, if your loop is long indexed, it's not a counted loop. So for I equal 1 to 3, where I is long, that save point polls on the back of every loop. So there's some interesting things. There's also things in the JVM that are stuff that it doesn't save point poll check on, like cloning a large object. You have to wait for that to complete. You could be, here's another really good one, is you're writing to a memory map file through a byte buffer, and you take a page fault as you write to that memory map file, and that page fault is queued up in the underlying block device waiting to go there. The entire JVM will wait for that to complete. There's lots of really, really interesting things. And including, here's a really nasty one. The JVM, when it's writing its own log, it writes that by memory mapping it. And as it writes the memory map log, if it ends up taking a page fault, your entire thing is stuck at save point until it's complete. So one thing, if you turn on your GC logging, what I like to do is I like to log to shared memory, or at least log to an SSD, and have something that copies it off elsewhere. That way you can avoid a lot of those sorts of pauses. So.
I listened to a software engineering radio podcast recently about LMAX. I think they said there that it was implemented in Java.
Yep.
I was just wondering where you found that sometimes C or C++ is actually faster, and one of the design goals of LMAX is to be as fast as possible. Why are you stuck with Java?
Yeah, good. So why do we do it? Quite simply, time to market. Really. So I love C++. I actually like C even better. I'm a bit of a heretic. I'm an older programmer who's been doing this for a long time. But if I'm honest, if I develop the same problem side by side, I can probably get the problem solved with a working solution in less than half of the time in Java than I can in C or C++. I can probably make the C or C++ one maybe 20% faster at the end of the day, but there's a big difference in cost. And that's not the language. In fact, I think Java is a bit of an abomination as a language. It's horrible, but it's got amazing tools. Like our IDEs, our testing frameworks, our mocking frameworks, our build frameworks, deployment, everything is so good in the ecosystem, and just access to knowledge, people, everything else. So it's kind of it is the world's worst language with the best tool chain and community around it. And that's what kind of keeps it alive and makes it very productive. Because there's lots to be very annoyed about it, but lots of the other stuff is great. Like you use something like IntelliJ IDE as your main IDE, and then you go and you work on some C++ or whatever, and you don't have access to it, and you're maybe using vi and meg files, and it's like, yeah, you can make it work, but it's a hell of a lot slower. Like debugging and stuff, now it's getting better in some of the native languages, but like some of our debuggers are wonderful in Java and stuff these days compared to like, if you're in an environment where you've got limited choices and using sort of like GDB and stuff, it's like, whew, it takes a lot longer. And actually, to answer your second part of your question on the GC, like, does the GC impact? Well, yes, it does, because if it's running in the background, it is causing your caches to be flushed and made dirty because it's doing stuff it has to. But you get a lot for it as well. Like, one thing is like, I think GC is wonderful, but it's like anything, use it in moderation. The way people can sometimes lean on GC like a crutch and just allocate stuff without thinking, like the number of strings and the stuff that we do. Like, I done a recent top 10 talk on things that I've seen that people make as typical Java mistakes that are typical bugs, and I showed it to a few people I know. One of the guys being Nissan Warcard, I don't know if you know him, he writes really quite cool blog. He's really, really sarcastic and quite funny.
What's his name?
But Nissan Warcard. So he writes the LumpSci Pi blog. It's based on Kelvin and Hobbes and stuff. He worked on Jesse tools, so some great implementations of concurrency tools out there. But he looked through some of my points and he goes, you kind of missed one of the really important ones. And I says, what's that? He says, I call it S3. And I said, well, what's S3? And he goes, the silly shit people do with strings. And like, we just do lots of really, really crazy things in Java with strings that waste an awful lot of time. Because one of the things is, if you allocate a lot, or if you copy a lot, what happens is you have to drag all of that data through the cache. And if you drag that stuff through the cache, when something comes in, something goes out. It has to be that way. So if you're just allocating in moderation and you're copying in moderation, that's kind of fine. If you do that a lot, you will end up washing everything else out. So rate of allocation does matter to your program because it will wash out your caches. But it's not to say don't do it, just like anything, do it in moderation. Any more? Yes?
I'm just wondering what your thoughts are on the pipeline architecture you went through for different stages. Trying to layer some sort of a priority scheme on top of that. Can that be done efficiently? Does it become counterproductive? You say that some traffic should be treated as higher priority.
Yeah, another excellent question. So like, we've got a pipeline, how do we deal with that from priority? We did a lot of work with CETA and different things, and what we found was at the end of the day, trying to do all of that scheduling and managing it always cost more than we ever got out of it. There's probably are some cases where it's worthwhile, but I very often find that trying to be smart with this sort of stuff always ended up losing in the end. Like all the designs I've seen that work really well are usually really simple, and quite often you can just change and tweak a few things here and there to get what you want to do. You sometimes want to have some sort of priority. You can do that quite easy by having multiple lines for the queues. Like you can just have even high and low priority. So between two stages is you've got the high priority queue and the low priority queue. And what you always do is you check the high priority queue first before the low. So something like that can be enough to actually deal with your priority cases rather than going to a whole process of scheduling. And having worked a lot on CETA and doing dynamic scheduling of that stuff, we found we spent far more time doing the scheduling than doing any real work. And it was just better to just focus on doing the real work. Okay. Yes?
Can you share any experience when you upgrade from Java 7 to Java 8 from a performance perspective? Was it a clear win, or were there certain edge cases that perhaps Java 8 suffered over?
So Java 7, Java 8, to begin with, I started at the very start before it went live, and on the whole, it was better. Early use of lambdas was a bit painful. We found that there was a lot of edge cases where things were allocating where they shouldn't have been allocating, and certain other problems. Over time, that's all seems to have stabilized quite well. I think it's now a pretty clear win for most things from what I've seen, moving from Java 7 to Java 8. being a performance win.
Are there any standouts in terms of the edge cases?
Not that I'm really seeing now so much. When you mean edge cases that are much better or edge cases where it's worse?
Edge cases where it's worse.
Some early stuff around hash maps had a few problems, but that's all pretty much fixed now, I think. So none that have really been me. I kind of subscribe to Dave Foley. Has got a good description of, like, he now calls himself a reduced instruction set programmer, and I think I'm very much rapidly becoming that as well. You see, most of my code, I don't use an awful lot of libraries, I don't use a lot of complexity, so I don't tend to tread into many weird things very often, and so I just don't tend to see. I see sort of people come up with these esoteric cases, and I keep thinking, how did you ever get there? Why are you using these things in the first place? And so maybe I just don't tend to wander off into those things. Yes?
Do you have any experience with the canonical queues? Have you ever compared them to Aaron?
Chronicle queues and Aaron are quite different things. So, like, if you're going to send between, so they come from different sort of backgrounds. Chronicle is about logging. Aaron's about messaging fundamentally. And particularly on the multi-producer side, Aaron has had probably much more attention on that. Chronicle, from my own experience, works very well if you have a single producer to single consumer. You start going to multiple producers or multiple consumers, it's not quite designed for that, and it's kind of a different background. The bits that I've used, I found that it suits certain circumstances. I don't tend to work in areas that requires that, because we tend to gravitate into your own specialty. So I wouldn't say they're actually a like-for-like comparison. They do different things.
But they're both like off-heap type of like structures, right?
Yeah. A tractor and a Ferrari are both automobiles. Not one's good and one's bad. One's good on a track, one's good in a field. But I think they're just quite different. Yes, they're off-heap. They're off-heap because, not because they deliberately set out to be off-heap, they're off-heap because Java has currently got missing features that hopefully in the future we're going to have addressed. So like some of the changes coming in Java 9, the enhanced volatiles, the extensions to byte buffers and stuff, a lot of the stuff could be starting to get much better, and a lot of what we do off-heap wouldn't be necessary anymore. I'm kind of looking forward to that. I think it'll be a good step forward.
Sorry, the last one. What are it's still kind of undecided with the fate of the unsafe. Is it still?
Oh, there's an official position now. So the official position is the desire is to deprecate all of the internal packages, so not just unsafe, but all of the internal packages. Some of the packages have been deemed with the state as being critical. By critical, they mean that it is required that there needs to be a replacement. So the goal, the plan that's going to happen is that things will be flagged for removal. There will then be an alternative created to them. Once the alternative has had at least one major generation, so like say Java 9 to Java 10 to bed in, there's a possibility it can be removed in a subsequent generation, but you've got at least a generation to pick up the alternative, and the alternative should have everything that's required to replace it. So some of the stuff's like really simple, like the fact that you want to sort of deal with you encoding base 64 and stuff like that, where some of the stuff is internal. Like for me, unsafe is a biggie, but also things like signal. Like the fact that you can't control C a Java process, it's just like, what year are we in? So you can do that by picking up some internal APIs. Those sort of things should be public APIs that are supported, that we can do, like things that it just any C and server application should be able to do these days. Yeah.
You said you work with a tool. Do you input developing versus off-peak, right? So do you end up wanting to have like the pulse collectors, or is it like can you do primary CMS type of stuff? Since most of your data is presumably off-peak.
So the main reasons I end up dealing off-heap is for probably two major purposes. One is to communicate between different processes. So like, we don't have a clear means in Java of doing that without going to the TCP stack. And sorry, that's just not acceptable on a modern machine as a means of communicating between processes. We need something better. We need shared memory. That's what's required. So you end up going off heap for that as probably the primary goal. And then the other goal that you use for going off heap is to control layout. It's not about avoiding the garbage collector, it's about controlling layout. You start dealing with very large data sets, you need to deal with the layout in a predictable manner. Like, you need to work with the prefetcher so you can stride through stuff. You need to be able to deal with stuff by dead reckoning so you don't have data-dependent loads. Things like object layout will address a lot of those, so that would be another reason not to need to go off heap. So I think a lot of things that people do is because we have missing features, not because they just want to do it. And if we address a lot of those things, we'll be able to do these. You can't deal with really large data sets in any sort of sensible manner in Java because of how objects are laid out at the moment. It just, the walking of the graphs. You can't build interesting data structures at the moment.
So, based on your experience, have you given any thoughts? You were talking about reduced instruction set programmer. Based on your experience, have you given any thoughts as to what functions or processes, what hardware implementation would be able to help you? For example, like the zeroing of the memory, maybe that is one of the things that can help improve performance.
Yeah, so that should be improved. I think we have features in the JDK that lets us do that. We just need to have really good implementations of some of that. I would personally like to see better support for vectorization. Because if we want to get our single-threaded performance up, the best way we can do that is with SIMD instructions. And having algorithms that can support that. Like, I think it's kind of crazy in 2016 that JavaScript now has support for SIMD and Java doesn't. Like, really.
One of the benefits of the disruptor, in addition to passing data quickly between threads, was that it allowed you to organize multiple threads so you can set up a pipeline, each doing its own step of the work. Whereas the queue replacements that you discussed, like the many-to-one concurrent array queue, good for producer and then consumer. Have you come across other paradigms that might work better than a disruptor for coordinating work between multiple threads, the way that a disruptor can with multiple handlers?
Yeah, so that's actually deliberately in Aeron. So in Aeron, you can have multiple subscribers on the same stream, on the same machine or across machines, and do those sorts of things. And it's actually even lower overhead than the disruptor. So yeah, it's been built in. It's a very common pattern. So like, quite often we want a sequence stream of events, kind of event sourcing. And rather than having multiple threads bang on the same model, we've got huge amounts of memories in our machines, huge numbers of threads can run at the same time. Just build multiple copies of the model. And that works really, really well. It's dead easy to test, dead easy to reason about. And you can even build different versions of the model from the same stream of events very easily. You just need to be able to replicate the events to them all very, very efficiently. So like, a lot of the focus on Aeron is multicasting on box and multicasting across box. You can do that. Like, I would actually like to get to the point where we've got a feature with LiDAR called, we're nicknamed it multi-channel cast, where you can specify multiple channel endpoints and send to that. So imagine you're in Amazon, where multicast network traffic is not allowed. But you can have multi-unicast streams going to the different endpoints, and will arbitrage the cost. So that if you were using a TCP socket, you have to send to every single one of them, and it all becomes a bit of, you have to have the data structures, the buffers, all of that duplicated. Our data structures, the CRDTs, are immutable in their nature, so we can use the same data structure to go to multiple endpoints. If you then take advantage of Linux features like send them message, we can send to multiple endpoints with the same buffer in a single system call. So these things start to become possible. Now, I'm going to have to do native stuff. Like, this sort of stuff should be starting to come into Java. That's what I do. When people start asking for more syntactic fluff and sugar, really? Like, can I have simple stuff like, can I construct a string directly from a byte buffer, please? Like, before we add any more fluff. That's some stuff we really need. Can I go directly to a byte buffer from a string? Like, these sorts of things we should be able to do, yet we can't. And yet these are major limitations on throughput in so many of our systems. It'd be a lot nicer if we could. Yes?
If you did a benchmark test for single producer, single consumer in buffer, running on hyperthread, of course, they don't have cache component. So producer running on the same physical core, and consumers running on the same physical core, but they share all the resources and running on different logical cores in the type of environment.
So you asking,
Do you have the benchmark?
did we test across cores or with a hyperthread?
Yep.
Yeah, if you test with a hyperthread, you get a really silly high benchmark because you're just sharing via L1. I wouldn't offer those as benchmarks because I don't think they're realistic. They're kind of funny, but they
Well,
don't.
the numbers will be much better.
So the figures that I give are across cores. They're across cores shared via the L3 cache, rather than they're not doing tricks like staying on the same hyperthread and exchanging that way. If you're exchanging via the same hyperthread, you're talking about a handful of nanoseconds. To go between two cores, the absolute minimum time is a dirty hit between cores. It involves a snoop from the L3 cache. That is a 60 cycle cost. You need to take that as your absolute minimum. If you're doing tricks to beat that, you're just cheating. So I think you have to face that is the minimum true exchange between cores. And then if you're doing it across sockets, you need to add in the QPI cost, which is another 40 nanoseconds out of the way. Like if people are giving benchmarks that are lower than those numbers, then it's just rubbish. They're not. If you can get down close to those numbers, you're working at what the hardware limitations are. But if you're going less than that, you're not measuring what you think you're measuring. This Jen, you're first.
Silly shit people do with strings.
Yeah.
Do you have a paper on that or examples or?
No, that was just a joke of Midscience. But you do see things like people in loops constantly appending to strings and all sorts of. But if you've been out and you've seen a lot of real-world applications, you start to get horrified by the things you see. I'll give you an example of something I see. It's not a silly string thing, but it's a kind of silly ORM thing. I think ORMs drive some terrible behaviors. And I've seen this one example where someone had a nested loop and they were getting response times under load on their website going up to 40 seconds. And so we were profiling to find out what was happening, and it was just really obvious, it showed up at the top of the profile, that they were making 7,000 database calls per request, because the ORM made it really easy to make the call from inside the loop, and people just didn't see it in the code. I think almost like being exposed to some SQL makes you realize that you're actually making the call to the database. All I did was move this call, because it was retrieving exactly the same data every time, out to above the loop and hoisted it and called in. The whole thing was so much faster. You see nonsense like that all the time. But the thing is, like, yeah, people make mistakes. Like, I wouldn't judge someone for making a mistake like that. It's the not noticing that that's the mistake. And you find that so easy just by running a profiler. Like, we'll come in, we'll all have a brain fart someday and do something silly, but we should be testing, we should have a decent process to catch these things. And the fact that those are things that can go for months without being caught, that is into the silly shit. This question back there?
In your production environment, do you always switch off hyperthreading?
So do I switch off hyperthreading? It depends. It depends on the type of problem that you had. If you go back to like Nehalem, it was definitely worthwhile turning hyperthreading off for certain semantics. Up to the latest processors, hyperthreading is getting pretty good. And my recommendation is always measure. You see, sometimes having the extra cores does help you with your type of application, sometimes it hinders. And you really only know if you measure for yourself. I've found over time it's evolved more from, I would have leaned to turning it off, now I lean more to turn it on, but I always measure. And I'm finding now that having it turned on is generally the winner in the two for some of the things that I get to see. Don't know how does it fit with your own views.
So why do you consider 99% because the type and drops, you may be, the numbers may be skewed much, like 95%. Why do you cut off by 99%?
So the cutoff here was only for the sake of the presentation. I don't cut off, and I capture everything. But you look at the stuff below 99 percentile is usually your own algorithms and queuing effects. The stuff above that is usually systemics, and so you just investigate it in different ways. All I was doing was like, let's cut down the noise so there's less to talk about, because they only got an hour to talk about things. Absolutely would not ignore above the 99 percentile. It's only for the sake of the presentation.
One more question?
Yeah. Okay.
Yeah, now with the Aaron POS processes or not even POS machines, so that is there any consideration in terms of the fade, controlling the fading, the failover, and all redundancy?
So the version that's currently out there doesn't have clustering support for going across machines. The semantics that you get for a stream now is very similar to a TCP connection. It's actually slightly more reliable than TCP, but kind of think of it that way. If you lose the stream, you need to reestablish and start again. It's not a persistent stream. I have been working on a persisted, clustered, consensus-based algorithm that's separate. It's not open source yet.
So basically refile in that
Yeah.
case. Okay.
Okay, great.
Okay.
Thank you very much, Michael.